To continue our theme with solving and manipulating equations, we're going to focus today on literal equations or equations that are entirely variables, um, or equations that just have more than one variable, and how we're going to manipulate them, move them around, and solve for a specific variable, because this is a skill you need just in general in math, and one that we're going to be using heavily here in a bit when we do systems of equations. So a couple things to consider. We're going to solve by undoing. I know at the end of last semester we talked about multiple ways that you could go about solving an equation. When we're doing literal equations and it's just variables being around, so lots of times they can't be combined because they're not like terms. And it's very important to understand your algebraic steps and be able to solve this by undoing. So two important things to focus on are the inverse operations. That's how we undo things. We undo things with the inverse operations. So if you have addition, you undo it with subtraction. If you have subtraction, you undo it with addition, multiplication, division, exponents, and roots, and so on. Those are inverse operations. They're what undo each other. We also have to be very careful about what are like terms and what are unlike terms. So when we have a bunch of variables lying around, they're not always going to be able to be combined. So be really considerate of that. And like terms have to have exactly the same variable and exponent. Exactly the same variable and exponent. So these guys are like terms, x and x, a squared, y, y. These guys are not, x and a, w and w squared. That throws some people off sometimes. This is the same variable, but it's not the same exponent. W and w squared are different. They're non-like terms. So these are two things we have to consider, inverse operations and like terms. So let's just look at a few examples here. Here's an equation. It's got a couple of variables, and if I have to solve this for x, it's kind of like what we were doing in the last lesson about changing standard to slope-intercept form. It's very similar here, where for this example, where if I'm solving for this x, I would do the same things as if I were solving for x by undoing if this were a number, except the only difference is, okay, let's add 2 to both sides. Well, I can't combine 2 and u. So this is just going to be u plus 2 over here equals 2x. That's okay. And then I can divide by 2 since it's 2 times x. The inverse of multiplication is division. And I can divide by that. And I can say that u plus 2 over 2 is x. Now you could also say that u over 2 plus 1 is x. So that would be u divided by 2 and 2 divided by 2. Now you can do that if you want, or you can leave it like this. This is a perfectly acceptable answer, because this is no more simplified than this is technically. So that's what that would look like. Let's solve this guy for x. You're going to run into funny things like this. Well, since this is a positive m, the inverse of adding that m on is subtracting m. So I have to subtract m from both sides. And again, z and m are non-like terms. So it's just z minus m equals, and then this is a negative x. Negative x. So we do have one more step here, is to divide by -1 on both sides, because when we're solving for a variable, we always want it to be positive. So this negative x is unacceptable. We can divide by its coefficient, which is technically -1. What's that going to do? It's going to flip the signs of all these. Negative z plus m is the same as m minus z, if you'd like to do that. There you go. Either one of those is acceptable as well. These hopefully get a little bit more interesting as we go. They're all different types of examples that I wanted to show you. So we're solving this one for a. So it's a times m. It's just like how you would solve, 3 times a, but now it's, we divide by 3, right? But now it's a times m. Well, we're multiplying. The inverse of that is dividing by m. Right? So when you divide a side, you have to divide the entire other side. So when m is divided by m, that's just 1, because anything divided by itself is 1. So we're left with a equals, and then we have n plus p over m. just like we did up here. And you don't have to make this, that is equal to this, but you don't have to make it that. It's perfectly acceptable like this. So lastly, we're solving this for A. Again, we're just doing inverses, right? So if we're dividing by B, we can multiply by B on both sides. So B times U is A times K. Since we're multiplying, we can divide by K on both sides, and B times U divided by K is equal to A. Okay, here's an interesting one because A's in the denominator. A's in the denominator. How do we get it out? So first we'll take care of this guy by subtracting him. Since it's a positive B, the inverse of that is subtracting that away. So we have Z minus B equals M over A. Now A's in the denominator. How do we get it out? And whenever anything's in the denominator, we have to multiply by it. We do the inverse of dividing by it so that it can free it up. It's kind of like what we were doing with fraction busters last time, but watch what happens, okay? We got times A, so A divided by A is just 1, right? Because that would be MA divided by A, so A divided by A is 1. But we need to multiply by A. Can't just do it like this. We have to multiply times the entire side over there. Multiply times the entire side over here, and that gives you A times Z minus B. The quantity Z minus B equals M. Okay, now we're still not solved for A, but we're in a better spot now because it's not a denominator anymore. So if it's in a denominator, you have to get that term alone and then multiply by it so that we can get it in a situation like this. And now we can solve for A. So it's A times this quantity, and I can just get rid of that quantity as a whole. So divide by Z minus B, because this is some number. That's some number. That's fine. You can divide by that whole quantity. That's why we call it a quantity. That's what we mean. It's just some numbers, just some value. So A equals M divided by Z minus B. And there you go. There it is. So we had to get this A alone so that we can multiply by it. Since it's in the denominator, that gets it free. But now that it's free, I can free from the denominator. It's in the numerator now. And I can divide by this whole quantity to get it to the other side, because quantity divided by itself is 1. And lastly, here's another, it's kind of pretty similar to what we just did. In fact, I didn't even realize that I'd used B for this. We're solving for Q here. So we can call this Q times T plus 1. Oh, should curve that. Equals R minus B. And again, since this is a quantity, T plus 1, we can divide by that whole quantity. And we get a nice little Q equals R minus B over T plus 1. So the whole idea of what we're doing here when we're solving literal equations like this is we have to use the inverse operations. It's just like if we were doing it with numbers, except we won't always be able to combine them because they're not like terms. Like, look at this. It is, I subtracted B. Normally you'd be subtracting like, oh, minus 5. Okay, whatever this minus 5 is. But it's not a real number. So we have to say R minus B. We have to keep them separate. And that's just something you got to get used to the more you work with it. But it's all the same algebra steps that you're used to. You just might not be able to combine them. You just got to keep track of where everything is as you go.